Today, we are going to tackle a skill that, let's be honest, trips up pretty much everyone at some point, from students to actual scientists. We're talking about measurement. But it's not just about getting the numbers right. It's about really understanding what makes an answer truly correct. So let's dive in. So what is the difference between a right answer and a wrong one? I mean, it sounds like a trick question, right? You do the math, you get the number, you move on. But what if I told you that the biggest difference, the thing that really separates right from wrong, often isn't the calculation at all? Yep, it's the units. You can have a perfectly calculated number, but if the units are wrong, the whole answer is wrong. It's a tiny detail with massive consequences. So let's make sure we nail this every single time. To really get our heads around this, we're not going to start with some complicated formula. No. Instead, let's use a super simple but really powerful analogy that just makes the whole idea of unit conversion click. It's really as simple as repacking boxes. So picture this. You start with 2 big boxes. You know that each one of those can hold 10 smaller boxes. So what happens when you unpack them? Well, you end up with 20 small boxes. The amount of stuff you have is exactly the same. All you've done is change how you're counting it. And that right there, that is the absolute core of unit conversion. The value itself, the actual physical amount of whatever you're measuring, stays exactly the same. We're just swapping out the label, the name we use to describe it. Okay, so with that big box idea locked in our heads, we can now move from that simple picture to the formal rules that really power all these conversions in science and math. You gotta love the metric system, right? It's used almost everywhere in science because it keeps things so beautifully simple. You can see here whether you're talking about length, mass, or volume, every single conversion is just a matter of multiplying or dividing by 10 or 100 or 1,000. It's a clean, logical system, and it's designed to make our lives easier. So here's the rule that does all the heavy lifting. If one of your big units equals, say, k of your small units, then to convert any amount x, you just multiply x by k. This is the engine behind every single conversion we're going to do. All right, time to put this into action. Here's a classic. Take a second and think about it. How many centimeters are in 3.5 meters? Think of this as the 2 parts of your brain working together. On one side, you have the long cut. That's the formal math, 3.5 times 100. But on the other side, you've got your quick check. That's your intuitive safety net. Just think about the boxes. You're going from big meters to tiny little centimeters, so of course the final number has to be bigger. It's a simple check that tells you you're on the right track. And boom, there it is, 350 centimeters. The formal math and our quick box check lead us to the exact same place. Perfect. Okay, let's flip it around and try one going in the other direction. This time, we're starting with a whole bunch of small units, grams, and we want to figure out how many big units they make up. Same deal as before, just in reverse. The math on the left is a simple division, 4,500 divided by 1,000. And our gut check on the right confirms this. We're packing a ton of small units, grams, into fewer, bigger units, kilograms. So yeah, the final number has to get smaller. And the answer is 4.5 kilograms. See how that quick mental check helps you know instantly whether you should be multiplying or dividing? It's a fantastic habit to build, like a built-in error detector. So we have the number. We're done, right? Well, not quite. Now we get to the next level. In science and engineering, there's another really important question we have to ask about our results. This is where we go from just getting the answer right to getting it professionally right. We need to talk about something called significant figures. So, significant figures, or sig figs for short, are the digits that actually carry meaningful information about how precise a measurement is. And for a doctor calculating a medicine dose or an engineer designing a bridge, this isn't just some random academic detail, it's absolutely critical. This shows the idea perfectly. On the left, imagine you use a basic school ruler. You measure something and you say, it's about 2 centimeters. But on the right, you use a much more precise tool, like calipers, and you get 2.0 centimeters. That extra zero isn't just there for decoration. It's a promise. It's telling you that your measurement is accurate all the way to that first decimal place. And this brings us to the golden rule. Your answer can never pretend to be more precise than your starting measurement. So, if your instrument tells you something is 2.40 meters long, that's 3 significant figures of precision. When you convert that to centimeters, your answer must also have 3 significant figs.
And that's why we write it as 240 with a decimal point at the end. That little dot tells everyone that the final zero is a measured, significant digit, not just a placeholder.
Okay, we've covered a lot. Let's bring it all home and wrap up with a quick guide to dodging the most common pitfalls, so your work is always polished and, most importantly, correct. Honestly, this is the #1 error people make, but you now have the ultimate fix. Before you even touch your calculator, just ask yourself that simple question from our box analogy. It will instantly point you toward either multiplication or division. No more guesswork.
All right, here is a final challenge, a great thinking problem that pulls everything together. You've got a rectangle with sides of 3.0 centimeters and 4.0 centimeters. So why is its area 12 centimeters squared and not 12.00? Okay, let's walk through the strategy. First, look at the sig figs in your inputs. 3.0 has 2, and 4.0 also has 2. Easy enough. Now, here's the key rule for multiplying or dividing. Your final answer cannot be more precise than your least precise measurement. Since both of our inputs have 2 significant figures, our answer can only have 2. That's why the area is 12, not 12.0 or 12.00, because those would be falsely claiming a higher level of precision than we actually started with.
So, to make sure this all sticks, I'll leave you with one last question to chew on. If you convert 1.2 kilometers to meters, should that final number get bigger or smaller? Just think about the boxes.